Good morning, everyone, and thank you very much for giving me the opportunity to talk today. I'm Filippo, and I'm currently working in two labs. The first one is my good lab, which is quite a big lab focused on synthetic biology and genetic engineering, and mainly specialized on the experimental part. And the second lab is Noelia Ferro's lab, and this lab is focused on developing methods for AI and protein design. Today I will speak more about our work on using reinforcement learning to guide protein language models, but also I will briefly talk about how we can use these methods to extract features. As the previous speakers very well explained, what is like the normal steps during training protein language models. Normally what we do is pre-train a model with the objective to predict the next token, and then after we have, after many GPU hours later, we have this model that we want to fine-tune, giving some sequences that are belonging to the family that we are interested into, in order to extend the family of the proteins that we want to study or synthesize, in order to give the model the ability to generate high-quality sequences. Our lab trained different models, specifically ProGPT-2, which is a decoder-only model that can sample from the protein space and generate sequences with low sequence identity. Then Zyme Control, which is a decoder-only model that is conditional, so we can give as an input enzyme class. And this model can generate sequences that belong to this enzyme family, broadening the family that can catalyze that specific reaction. And more recently, we trained also RegZyme, which is an encoder-decoder model that can take in input any reaction and gives us an input string of amino acid that potentially catalyzes that specific reaction. Today, I will focus more on Zyme Control, which, as I said, is a decoder-only model, and take as an input an EC label. And EC label is like a hierarchical classification of a specific enzyme class. And given this input, it will produce many sequences in short times. These protein language models work quite well, are able to produce proteins that has activity higher or like wild type, or even proteins that are more thermostable and has higher pH stability. For now, like everything looks great, but then of course there is a downside. So if we compare the distribution of the outputs and the distribution of the features of the training set, the two completely match. So this is true, for example, for the sequence length, for the TLDT, for the activity, and for also the TM score. This situation is far from being ideal, because in case of protein design, we want to sample proteins that are very rare into the protein space, that have very high features, for example, very high activity. And then if we sample from such distribution, and we want to sample very rare events, would take a lot of compute to sample these elements, if ever this is possible, actually. So for this reason, we are recently introducing reinforcement learning in our pipelines. And we can picture reinforcement learning as a process where an agent, in this case a rover, takes through the interaction with the environment. In this case, we want to go from point A to point B, and each action that the rover takes will have an effect. And the objective of the rover is to maximize the reward. So if we take this and we put it into the protein design, we can have an agentic view for protein design, where our agent, or our protein language model, generate many sequences. These sequences interact with the environment, and we can retrieve a score that could be experimental, but also in silico. And this pair of genotype and phenotype, or genotype and score, can be coupled and feed back to the model in order to maximize that specific feature that we are interested into. To do this, we are applying directed preference optimization that was designed for large language models with this specific, let's say, variant that has been developed in the HE lab. And in this case, we are taking into consideration multi-objective scoring function that associate to a specific sequence. Yet we don't want to forget all the knowledge, all the underhood, let's say, grammar that was learned before in the costly pre-training. So we started with a simple objective. In this case, for example, when we give a specific label for carbonic anhydrase, the model is able to produce 60%, in 60% of the cases, a specific carbonic anhydrase, which is beta carbonic anhydrase. And only 20% is able to produce alpha carbonic anhydrase. So in nature, there are 8 different folds of a carbonic anhydrase, and our agent is mainly producing beta carbonic anhydrase. The objective in this case was to reverse this ratio, and we set as a reward function the TM score. TM score is a score that it's retrieved when you superimpose 2 proteins, and if the and if this TM score is more than 0.5, then we consider that the fold is basically the same. And as you can see here, over iterations, we have an improvement, and most of the sequences are alpha carbonic anhydrase. This without affecting negatively the number of clusters or the sequence identity produced. We tested this for many different features, bounded or unbounded values. For sake of time, I will not spend too much time on this, but what I think is very interesting is that actually we observed that this reinforcement affects not only enzyme classes that are objective to the reinforcement, but also classes that are close by, let's say, that specific enzyme class. Giving this like a good opportunity to, like in case you don't have many data points for a specific enzyme class, maybe we can reinforce the neighborhoods and then get the benefit of reinforcement learning from the neighborhood enzyme classes. We then decided to go a bit further and make the reinforcement a bit more complex. And in this case, we produce, after fine-tuning, 3 binders, and we participate to Adaptive Bio Challenge. And in this case, the objective was to design binders for EGFR, which is a carcinoma-associated protein. We fine-tune Zyme control, and then we produced and tested the proteins, and we got 3 binders that has wild type or higher than wild type activity. We use this experimental value to reinforce the model, and we achieve in just 1 iteration 1 binder that reached 27 nanomolar binding affinity. This with a reduction of sequence identity, and 4 out of 9 binders had affinity, like higher affinity than the best binder of the previous iteration. What I found very interesting is actually the fact that you can also extract features from this reinforcement learning campaign. So if we compute the log likelihood of each token of the model that we aligned, and we subtract the log likelihood of the model of a reference, we can retrieve an intrinsic reward at the token level. This intuition was made in this paper from Rafael, where they studied this possibility of retrieving an intrinsic reward from after applying DPO, and which is quite surprising because DPO takes an input, a sequence, and a reward, and doesn't have like awareness of the token per se. But yet, after alignment, it's able to retrieve and understand mistakes in the text and align like pinpoint mistakes where there is, like, in this case, a typo in the offer of, like, instead of 300K, 38K, there's a mistake and they put 250K. So we can do the same, but with the protein language model. So we can study, you can picture in this matrix where at each column it's the same amino acid repeated over many iterations. And the first row is iteration 0, so the model not aligned. And then we align the model step by step until we reach the last row, which is iteration 30. And as you can see here, the model understands and scores specific tokens in a different way. What I find also very interesting is that there is, we can show kind of inertia and some like patterns emerging, but also if we introduce point mutation into the sequence, the models is able to score that mutation with a lower reward. More recently, this work is made by one very talented master student in our lab, Gerard. We're also studying sparse autoencoders and how we can use this sparse autoencoder to retrieve information from these datasets. If you're interested into this, please come to visit our poster number 136 tomorrow, poster session 3. What is next? So currently, we're trying to reinforce using experimental values and trying to close the loop. So iterate in fast fashion production of sequences, scoring with experimental data and feedback the model multiple times. And this work is made by Maria and Edu, and they also have a poster, number 51, later, I think. And we're also trying to apply reinforcement in a bigger scale. So for example, starting from hallucinations and then reinforce to produce proteins that are binders, so protein-protein interaction, but also binding to ligands. In conclusion, DPO can optimize very complex multi-objective functions spanning from biochemical to structural. What I think is also very interesting that here we're reinforcing using syntactic data, which is will be very relevant in the future, where more and more data sets will be contaminated by syntactic data. Of course, the best environment where we can test our agent is the real world, so experimental data. And the interplay between experimental data and generative AI will be quite essential, I think, in the future, and will allow us to learn from the two worlds. Thank you very much. Again, thanks also to all the authors in the paper, Maria, Andy, Tlal, Noelia, and Mark. I hope I didn't forget anybody, and very happy to take any questions.